Hello, 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 hello. सौरभ कुठे गेला? Hello, hello, sir. Hello, hello, Mr. Alberto. Hello, Alberto. Hello.
Yes.
Good
Good
afternoon, sir.
evening.
Good morning. My name is Sachin Surve.
No, good afternoon.
Good afternoon, sir. Nice talking with you. Just I have started the system and 30 minutes,
Yes, I want.
yeah, 30 minutes or more as per our standard time. Still 30 minutes or more.
Okay.
So we'll have to wait
Yes. I think that it starts at 6:30 for me.
after 30 minutes exactly.
Mhm. Perfect. But before I would try to share my screen in order to be sure that
Take your
everything is okay.
guides to you. Just share you the screen. Just wait, sir. Please share your screen.
I think that you have to allow me.
Sorry.
I'm not, I don't have permission to share my screen, so you have to allow me to share.
Yeah, we can
Only,
share the your
only,
host now.
only the host can share in this meeting.
Yeah, you are host now.
Oh, okay,
Yeah, please share your
great.
screen.
So
Yeah.
perfect. So let me check.
Hello?
Yes, Doctor. I'm sorry. I have a problem here with my drive. Mm, do you mind if I share with you the file?
Sorry? So, you are the host, you can share the screen, sir. Hello?
Yes, Dr. Christian. Just give me a second. I'm trying to solve the problem here.
Yes, yes, yes. Okay. Any problem is there in your system?
I'm sorry. I can hear you clearly. I'm not. Let me check my.
Just click on the share screen.
Yes, my drive. Dr. Christian, can you see my screen?
No, I can't see your screen, sir. Dr. Krishnan yet to come because still there is a time.
Just
Have you opened your presentation? Hello?
pardon?
Have you opened your presentation?
Yes, I can't open the file. But it's okay. I think that will be better if I share with you the file, like a PDF. Let me send you the file to your email, Dr. Christian, if you agree. And if you could help me. Um,
What is the problem there? Your PDF file is not opening.
just give me a second. Okay. Dr. Christian, do you mind if you share for me the slides?
Dr. Krishnan still not come.
I can't hear you clearly. I'm sorry.
Still Dr. Krishnan did not come in the system. Any problem with you, sir? Hello?
Hello.
What is the problem, sir?
The problem is that we are in Zoom, right?
Yeah, you
So
are in Zoom. Yes.
I work in I'm working in Linux, so I can't work from my computer at this moment. So I'm working at this moment. I'm working from my tablet, but when I ask my tablet to connect to my drive, I can't do it. So I think that the best answer at this moment could be to share with you the PPT, and if it's able for you to share
Is there a time you
to
can,
pass.
so you can join the Zoom?
I'm sharing with you in the by WhatsApp the
Okay,
presentation.
because you are the host. You are the host. I don't know how we can join it. No presentation.
I can't.
You are the host, so I given right to host. Because if I become the host,
Dr. Christian, I'm sorry, but I can't understand what are you telling me. Hmm.
let me check. Let me check. Sir. Wait. Yeah, let me check, sir. Uh,
Okay.
Hello.
Hello.
Just start the green button, share screen. It will come, sir. There is no issue in the Zoom.
Just give me a second. I think that I get the solution.
Yeah.
Give me just a second.
Yes, yes, yes.
Just a minute. Just a minute.
So it's a PDF, no?
Okay,
Yes.
we got it.
Wait, wait. We can. It will slowly. Yes, it is come, sir. Hello.
Okay,
It
okay,
is come.
pretty
Fine,
good.
fine, fine.
I'm
Yes.
sorry, it was a code that they was sending me
Sorry.
to my email to my they were sending me a code and didn't see that the code. So I'm sorry, but now it's okay.
Yeah, it is okay, sir. Just scroll down. Just move it. You go to next slide. हो गया सर, हो गया, चालू हो गया।
Yes.
अभी उसको मैं रोहित
Pretty good.
लग गया सर वीडियो।
Yeah, Alberto, good evening.
Good evening.
Yeah, Dr. Krishnan here.
I'm so sorry because of the delay, but I think that we are on time, right? We start at 6:30, I think.
Yeah. So we are on time. We have almost 7-8 minutes.
I'm sorry, there is a sound in the
We have
bottom that I
almost
can.
Yeah, we have almost 10 minutes to start.
Oh,
So you are
pretty
on.
good, pretty good.
Yeah.
We are on time. Great. I just have a question for you. Can you hear me clearly? Because
Yeah,
I
it's very
can't
clear.
hear you clearly.
It's very clear.
Oh, perfect. Okay, thank you. Thank you, thank you. Mhm.
Hello.
Hello.
Yes, sir. Dr.
Just go ahead, please.
Dr. Krishnan is here.
Mm.
Yeah, I can see your face, sir.
There is something wrong with your audio because I can't hear you clearly.
I can hear you also clearly.
Yes, you hear me
Yes, I can hear you clearly,
in
sir.
a
Yeah,
clear way.
you are clearly. Yeah, you are clearly audible, Alberto.
You're
Yeah.
audible, sir.
No, I know that you can hear me in a clear way, but I can't hear you clearly. I don't know if it's your microphone or it's something related with the connection.
Sir, there is
Anyway, I'm ready.
Maybe you want
Just
to
tell me
log
when
off
to
and log in.
start.
You want to log off and log in again?
No. Hello.
No.
Yeah.
I'm happy. Don't worry. So
No,
let's
sir,
start.
don't log in. We'll wait for 15 minutes more. Still, there's a time. Dr. Krishnan will introduce it.
Yeah, Alberto, we have few more to join. Let's wait. Yeah.
Still, there is a 10 minutes more, sir.
Sachin, Nimesh is joining, na?
Nimesh is busy with some personal activity. After some time he will join. So uh, अभी मुश्किल से उसका पीपीटी लग गया
Very
है
good.
सर. I will not disturb him. डॉक्टर कृष्णन सर,
Yeah,
अभी
yeah.
उसको मुश्किल से पीपीटी लग गया है प्रेजेंटेशन, तो उसको डिस्टर्ब नहीं करेंगे.
Okay, okay, okay,
तो
okay,
जैसे 5 बज जाएंगे आप यू स्टार्ट द इंट्रोडक्शन एंड यू विल कंटिन्यू द
okay,
लेक्चर.
okay, fine.
डिस्टर्ब
Yeah.
नहीं करेंगे हम लोग लेक्चर को, उसको पीपीटी
So
को.
Alberto, you first you take around 45 to 15 minutes for your lecture, okay? And
Perfect.
it will be followed by question and answer session. So people will be typing their questions in the session and which you can maybe answer later. At the
Pretty
end of
good.
the
My presentation lasts, I think, 45 minutes to 50 minutes.
Yeah.
So we have more than enough time to Q and answers session.
Yeah.
Great.
Alberto, are we good to go?
Sure, I'm ready. Just tell me when, and I'll start the presentation.
So I will give a brief introduction about you to the participants and
Great.
then yeah.
Wonderful. Thank you.
So a warm welcome to all of you, those who have joined today for this webinar on duplex stainless steel welding by Mr. Alberto. So let me introduce the speaker for today's talk. So Mr. Alberto is a very distinguished speaker. He's a mechanical engineering graduate from National University of Colombia with a master's in welding engineering from University of Peru. So he has been in this welding field for quite long. He has been working with various industries, and he is also a professor in one of the university. So he is an international welding engineer and European welding engineer, and also a certified welding inspector. And he has got quite vast experience in metal additive manufacturing, and with roles in independent consulting, and as I already told, as a teaching professional in the university. And he has been working at various positions in renowned companies like Linde, ISAP, and he has contributed significantly to various international projects, and also quite large contribution in the area of laser welding. So it is our pleasure to welcome Mr. Alberto on behalf of Indian Institute of Welding, and let us all hope to have a wonderful session in the next 1 hour. So over to Alberto.
Well, thank you very much. I'm very glad to be here with you today. Thank you for your generous presentation. And thank you again, Dr. Christian Shubarana, for your kindness. This opportunity is very insightful for me. So let's talk about duplex stainless steel welding. As the title says, it's just a review. We have a lot of things to say, a lot of things to review about this endless topic. As we can, we'll see. There are a little different details to consider in order to obtain solid weldments in duplex. Of course, there are a lot of different alignments in this family. So I want to share with you the most important highlights in this topic based on my experience. But of course, as you know, in welding there are no experts. We learn from each others, and I just want to share with you part of my modest experience in this field of welding. So let's start. First of all, I think that every welding process is around this graph that I have called virtuous welding graph, MPDP, which is related with four. It's a three-dimensional solid. It's like a kind of tetrahedron. So we have four main topics here, and if we consider very carefully each one of these points, we will under control every welding process. So the first point is, of course, material. And when I talk about material, I'm talking about base material and also filler material. But of course, we have to consider all the materials that are processed, transformed during welding, during our welding process. Second, we have the process itself, which means all related with the equipment, all related with the technological aspects of the process. Everything related with cutting, with polishing, with grinding, everything related with processes, with transformation is in this point. Third, of course, we are related with personnel. And in this case, when we talk about duplex stainless steel, the personnel is very, very important. Is very important. And finally, we have the last but not the least, the documentation. Documentation is very important for us because there are a lot of different tests that we have to carry on in order to obtain a good qualification of our procedure, our BWPS. Documentation in this case, well, always is important documentation, the standards, specification, codes, etc., in the welding world, but in this case, with duplex stainless steel, is even more important. So I want to share with you two phrases, two sentences that I consider that are quite important for understand this topic. And the first one is, the best weld is the one that doesn't exist. Why? Because we have a beautiful raw material and a beautiful base metal with enormous advantages, but we partially destroy these beautiful properties. So our idea, our goal, our challenge is how to weld, how to process this duplex stainless steel with the less damage possible. This is our challenge, and this is what I want to share with you today. And the main idea is to control the welding process. I mean, every detail is important in duplex stainless steel, as we can see in a moment. So in that sense, I want to develop today, I want to share with you, I want to present to you 5 concepts that I consider that are quite important in this topic. First of all, the relevance of the shielding gas with or without filler metal. The second one is the initial and the final austenite delta ferrite ratio, which is essential in this process. In this material, it's to maintain this ratio is essential for us, and we will see how to try to maintain this ratio. The third one is the heat input, of course, and its relation with the cooling speed and the final properties. The fourth is the base metal. Try to understand what happened in the weld metal during the thermal cycle, and what happened in the fusion zone or in our weld metal, and what happened in the heat affected zone in terms of the changes, that the chemical changes that have place in the during the thermal cycle. And finally, I want to share some ideas with you about the use about the constitution diagrams prediction or estimation, and how can we measure or estimate this ratio between austenite and delta ferrite. And as you can see, the nitrogen is the key in this family of alignments. I think that Balakrishan Sudra Rahan has raised his hand. I don't know if we will deal with questions during the question and answer session, or do you want to participate right now, Balakrishan? Okay, so let's go ahead and let's start. Okay, let me start for the end. Here we have some kind of relationship between these previous key concepts and the final results in terms of the corrosion resistance and the mechanical properties, not in the base metal, but in our weldment. Remember that we have a set of pretty good properties, and we damage. The thermal cycle is deleterious for these properties. So the idea is to maintain those properties at the highest level possible. So the first key concept is the nickel in the filler metal. Maintain this idea in your hand. Nickel is important. The second idea is that nitrogen is quite important. Nickel is important. Nitrogen is quite important. Second, the proportion, the ratio delta ferrite austenite is absolutely fundamental. It's critical for not only for the mechanical properties, but also, and even more important, for the corrosion resistance. Okay, good. Then we have to work with actual values of heat input. This is the third basic idea. The fourth is that we can estimate, we can do a prediction of what it's the final result before to weld by the use of the constitution diagram, but we have to be clear how and which constitution diagram would be used. Okay, and finally, the what happened with the chemical composition? Can be changed the chemical composition before the welding? Okay, and the result is changes in the corrosion resistance and the mechanical properties. Okay. Okay. Well, what is a duplex stainless steel? This is a pretty simple question. It's a in general terms, it's an alloy made by the combination of two phases, of course, ferrite and austenite, which means a solid solution in iron alpha, or a solid solution in alpha gamma, in iron gamma, right? Okay, so we are somewhere in between of these two words of the advantages and the disadvantages between the ferrite and austenite, but with enough alloyments, with enough alloy elements to consider that this alloy is stainless steel. And this is quite important for us because the corrosion resistance is very different, I'm sorry, if we compare the ferrite and the austenite. The problem, the weakest point for us is the ferrite, and unfortunately, in the middle of the screen, in green, the green line represents a typical ferritic stainless steel. It has a good good properties, for instance, in terms of stress corrosion cracking. It is ferromagnetic, but his resistance is not the best. The elongation is lower than the red line, which represent an stainless steel at 304, one of the most and well-known stainless steels that we use. And in blue, we have a hyper duplex stainless steel. So we can see here that we have a higher strength in terms of the tension resistance, the ultimate strength. But the elongation is the percentual elongation is not the best. It's more related with the ferritic stainless steel than the elongation of austenitic stainless steel. Okay, so when we study under the microscope this alloy, we see whether you looking, whether you can see in the right corner, in the upper corner, We have theoretic phase and austenitic phase. This photo is this micrograph is it's very well obtained. I mean, has this material has a high corrosion resistance is quite difficult or could be quite difficult to obtain this kind of quality in our micrographs. And this is very important, as you will see in a moment. My first, okay, here we have a very simple figure in which you can see the chemical composition. We can see, for instance, the difference in chromium. This is I took this UNS S30 2707, which is hyper duplex stainless steel, and we can see here the difference in chromium. We have almost 30% of chromium, between 26 and 29% of chromium. And nickel is not the best, is lower than 304L, but we have high nitrogen. Remember that the key concept here is the role of nitrogen and the role of the nickel. Okay. Of course, we have a very, very low quantity of carbon, which is 0.03. It's a good quantity, as we will see in a moment. It's very, very low, and we need a very, very low amount or a quantity of carbon, because we don't want to obtain carbides. If we control the carbon in our alignment, we are controlling the probability to obtain deleterious phases as carbides. Okay, good. Here we have a typical image about the anisotropy present in this kind of steel. As you can see here, the direction of the process lamination, the lamination process, is quite evident. This is taken from a real sample of hyper duplex stainless steel, and one good idea is to maintain a strict control in the shop about the material that we are keeping there, in order to have in mind what is the direction of the lamination of our material. This could be very important in some cases. Of course, it's more important in plates than in pipes or piping or tubing, for example. Okay, and one recommendation is to work with actual values. I mean, to work with a chemical composition that we have made directly with the material that we are working with, because there are of course difference between the nominal values, the mill certificate, and the best to obtain real results, to good results, is to work with actual values, with real values. So my recommendation is to take a chemical composition, to do a chemical composition and work with these values. Okay. There is a misconception about the duplex stainless steel. The misconception is that the duplex stainless steel has 50% ferrite, 50% delta ferrite, and 50% austenite, and that's not true. For instance, ABWS D10.18 show us that it's accepted for the base material. It's acceptable a delta ferrite percentage from 25% to 25% to 75%. Okay. And NACE in a recommended practice talk is about 30 from 35 to 65 delta ferrite. So it's not true that a good base material have to have 50% ferrite and 50% austenite. That's pretty hard to obtain and is almost impossible to obtain during the welding process because there are a lot of different variables to consider. Okay. Okay, let's take a look at the alloy family. It's the relative extense family, which started with just three alignments, three alloys, three products. At the very beginning, they couldn't be weldable because the idea was to use this kind of mix between ferrite and austenite as a material to castings. But the ratio between ferrite and austenite was obtained or is obtained because these alloys are useful today. Is obtained through heat treatment. Okay, heat treatment that it's quite simple for a casting, but almost impossible in practical terms for weldments. Okay, because normally this heat treatment implies to raise the temperature up to 1000 Celsius degrees, and it could be economically impossible to treat each weldment in every joint in a weldment. Okay. First of all, we have to say that this family is organized based on a concept which is called the PREN. This PREN is a relative number, is undimensional, that give you an idea about what is the resistance of this specific alloy in front of the pitting corrosion. Okay, so PREN means pitting resistance equivalent number. Okay, and it depends on three values: the percentage of chromium, of course, because if we remember, the chromium oxide is the skin that protect our stainless steel. Okay, molybdenum, which is of course improve the corrosion resistance, and nitrogen, because nitrogen is a stronger stabilizer of the austenite, and austenite is more resistant than ferrite. Okay, and it's more stable in front of the corrosion, in front of a corrosive environment than ferrite. Okay, so the PREN, it's fundamental in to control, to understand what happened with this kind of materials. And so if you see here in this table, which was taken from the Nickel Institute, the first family, the first part, the first member of this family is the lean duplex. We have a big classification, which is the first and the second generation. The first generation, not weldable, only for castings on the ferrite austenite is obtained by heat treatment, etc. But in the second generation, which is a much modern alloy, start with the lean duplex. I mean, they are duplex, yes, but is the weakest member of the family. Okay, so if you see in the last column, you can see that we have the PRE, right? And more or less is close to 25. Okay, from 22 to 28, 27, I think is the highest. Okay. What else? Nitrogen is important here. If you see, nitrogen start from a very, very low value, 0.05 to 0, almost 0.3. So this started when technologically was possible for us to include nitrogen in the metallurgy of the steels. And did happen, I think, 40, 50 years ago, nothing more than that. Okay, perhaps in the 70s, in the 60s, perhaps. Okay. Okay, good. This is the first member of the family, the lean duplex. To calculate the PREN, the pitting resistance equivalent number, is this equation that we are showing you here. But there are a property or a disadvantage, an advantage, who knows? That depends on the application. This kind of lean duplex, if you see here, you have 4-6% of manganese. And the manganese has a very interesting influence in this family, in this member of the lean duplex. When we deform 30%, this kind of, not all the family of the lean duplex, but the lean duplex with high manganese, we obtain a transformation from austenite to martensite. A transformation from austenite to martensite. How many how much austenite is transformed in martensite? 50%, which is impressive. So if we don't take it in account, we can have a very fragile raw material, and you can't make a good reading of ferrite, for example, because of course all the martensite is ferromagnetic, as you know. Okay, this is quite interesting. And this temperature, because is this phenomena happening in a specific temperature, is calculated by the use of the percentage of carbon, nitrogen, silicon, nickel, molybdenum, chromium, and manganese. Okay, this is quite important in this case for this lean duplex. Okay, the second member of this family is the lean duplex, but containing molybdenum. Okay, if you see here, molybdenum is quite important in this case because starting 0.8 and finish in 1.8, which is a lot of molybdenum. This molybdenum, of course, has his own role in the alloy, and mainly help with the work under high temperatures. We will see that that we have some restrictions in order to maintain this kind of steels at high temperature for a long time. But molybdenum help a lot with this. Okay, good. The third member is which we call duplex in general, duplex, which means standard duplex. Okay, in this case we have two alloyments which contain wolframium, okay, or tungsten, and of course it contains also nickel up to 7%, and a lot of wolframing in this case. So if we have wolframium in this alloy, we have to work with this PREW, which consider that wolframing has a role in the production, in the relevance, in how powerful can be this stainless steel in front of the corrosion resistance. Okay, and we follow with the super duplex. The super duplex is, as the name said, is a super duplex. I mean, if we check the PRE number in lean duplex, we were talking about 22, 24, 26, but in super duplex, we are talking about 40, 41, 42, okay, which is incredibly high, especially in environments with high chlorides, okay? And the top of the notch is the hyper duplex member, which is pretty I think so. I think someone has his microphone open, so please turn off. In hyper duplex, we are talking about 50 to 52, more than 50, which means that a hyper duplex has the double of the corrosion resistance than the resistance that have the lean duplex. Okay, which is quite remarkable because if we see here in this one, the austenitic family, let's take 360L, which of course has molybdenum, whereas 360L has a PRE equal to 24. I mean, 360 is quite important in terms of quite relevant in terms of his corrosion resistance, and a hyper duplex has the double resistance. Okay, and with the under a consideration very important in terms of money. If you see the quantity of nickel that has the 360L is 11, but hyper duplex only has from 6.5 to 7% of nickel. In fact, the promotion of this kind of stainless steel was done because of the crisis of nickel. The price of nickel was had a rise pretty difficult for to follow for the steel makers. So they started working again with this alloy and with this family of alloys, and it was a totally success. Okay, of course we have some most common duplex. For instance, and the 2205 is quite common to find it in everywhere, and we try to work with hyper duplex, but people is a little afraid uh, about how to use this kind of hyper duplex. There are there are a lot of misconceptions, a lot of myths around these steels, and I hope to help you to understand a little better how to use, how to apply, how to qualify this kind of steels. Okay. Well, let's talk about welding processes. In this case, all the processes that we use to process austenitic and ferritic stainless steel are able to be used with duplex stainless steel. So, which is remarkable because we don't have, in terms of technological weldability, we have the equipment, we have the gases, we have a lot of advantages that we develop for austenitic stainless steel. So in that case, it's quite simple or relatively simple to apply all this technology in terms of welding processes in the weldment of duplex stainless steel. So we can have pretty good with strip metal arc welding, gas metal arc welding, submerged arc welding, flux core arc welding, gas tungsten arc welding, bracing. Even bracing is possible to to be used with this kind of material. And it's quite remarkable and very useful. Okay, laser, electron beam welding, and plasma arc welding. Of course, we have laser with or without filler metal. We have electron beam welding with or without filler metal. We have plasma arc welding with or without uh, filler metal. And of course, I'm sorry, I'm confused. Gas tungsten arc welding with and without filler metal. Okay, some people believe that it's impossible, but it's not impossible. It's just a little more exigent in terms of the control of the parameters, the technological parameters, the gas, the filler metal, the control of the qualification of our process, the control all over the stuff, the welders, the tack welders, the supervisors, inspectors, engineers, everyone involved in this kind of process must be clear about which means duplex stainless steel. But everything is possible with a duplex stainless steel. I wish you maintain that idea in your hand. And very important, when we talk about GTADW, gas tungsten arc welding, in the case of duplex stainless steel, we talk about TAC, tungsten active gas, because by the addition of small amounts, small quantities of nitrogen, we are able to obtain a different microstructure. Because remember that the nitrogen, it's a very strong austenite stabilizer. Okay, it's very important. It's an active gas for us. And now we have today the sky is the limit with this duplex stainless steel, especially with the super duplex stainless steel, because Sandvik released to the market powder to be used in powder bed fusion laser beam in additive manufacturing. So that limitation that we had in the past about the base material in terms of plates, in terms of pipes, in terms of tubes, in terms of the material, to try to work with the material to understand it. Now we are able to print parts in super duplex stainless steel, which is quite relevant. But additionally, to powder bed fusion by the use of a laser, we are able right now, to print by the use of a technology called direct energy deposition, that I'm pretty sure you already know it, how it works. But it's simply the natural extension of arc processes applied to the additive manufacturing. Okay, So the sky is the limit in this moment. If you have a robot, if you have a SMAW, I'm sorry, GMAW machine, you are able in your shop to print things, parts, in super duplex stainless steel. Okay. Of course, in that case, we need to set up to uh, to develop a heat treatment to obtain the final properties. Okay, but it's quite possible. It's very remarkable. I think that Sandvik released this powder last year, maybe. Okay, perhaps. Okay, very good. So here we have some examples of this kind of products which are susceptible to be printed in duplex stainless steel and super duplex stainless steel. Okay, this is powder bed fusion, which is very fine. The appearance of the product, and here we have welding processes. I mean, this is direct energy deposition, which is to weld layers and layers and layers and layers and layers of welding in order to obtain base volume, which normally have to be mechanized by a traditional process in a CNC lathe or something like that. But it's very important. And here we have a macro showing us this is a research project from Bahid Hosseini from the Department of Engineering Science in, of course, Sweden, in Trollhättan. Very good. So as you can see here are layers and layers and layers of welding in order to obtain a block to obtain then to obtain a piece. Yeah. Okay. Now let's talk about a little about the filler metals. The problem, if you remember, the problem that we have is that it is not possible to maintain the initial properties in the base metal. Okay, so we have to add some. We have to yes, to add a little more nickel. Remember the two main elements here in this history, nickel and nitrogen. So we have two options: to add nitrogen up 2% of nitrogen, and we will see why we use 2%. Yeah, yes. Something is asking. So someone is talking.
You can go ahead. I think it was some noise. Yeah.
Okay, thank you. So if we use filler metal, we add from 2% to 4% of nickel. Okay, in the filler metal, because nickel promotes the austenite. Okay, and remember the key here is austenite. We love ferrite, but we do really need austenite. Okay, very well. And if we are not using filler metal, which is possible, we have to add 2% of nitrogen in the shielding gas. But not only in the shielding gas, also in the vacuum gas. Okay, it's very important. There are a lot of literature that told you that you can use 10% of hydrogen, 90% of hydrogen, which is very, very dangerous because mm, a shielding gas with more than 5% of with hydrogen is considered flammable, and flammable means explosive. So it is much better to work with nitrogen with 2% of with nitrogen valence argon. Okay. What about the filler metal? How can we select our filler metal? It's quite simple. It's quite simple. Doesn't matter if you talk about ESEV, if you talk about Certilas, if you talk about Sandvik, whichever, everyone will offer to you an alloy with more than 2% or 4% from the original value of nickel. Okay, this is the key. Okay, nickel 2%, 4%. That's all. They have it. We have very clear. We know which filler metal uh, able to have a good response with that kind of which a specific kind of duplex. Okay, so to select the filler metal is not the problem. We have enough information about that. Okay, so don't worry about the selection of the filler metal. There are a lot of information about that. Okay, very good. So for instance, in that case, we have 9% of nitrogen, of nickel, I'm sorry, which is higher in 2%. Okay, very good. Let's check one or two products about ESEV, and they have a line of products called Xeton. Okay, so Xeton is the same. Look at that. Nitrogen, 8.5% of nickel. Okay, that's all. Of course, they have manganese, they have very low carbon, 0.040. Okay, someone can't hear me. Can't you hear me?
Yeah, it's clear. Yeah.
Okay, thank you. Okay. So we have even less carbon in order to limit the probability to obtain carbides. Remember that in this case, well, we have a problem with stainless steels, right? Which is sensitization. Sensitization means that in a specific zone, the chromium aim to be used in the protective layer was used to construct a chromium carbide. So this chromium, the plate of chromium, a little zone, and normally this is localized in the grain limit, which is a very, very big problem for us. Okay? So in this case, we have the same problem. We could have the same problem. So we don't need high carbon, okay, in our alloy. So this is the reason, because the filler metal have even less carbon than in the base material. Okay, and if you see here, we have a number called EFN. You have carbon, manganese, silicon, sulfur, phosphor, nickel, chromium, molybdenum, copper, nitrogen, niobium, and PRN, pithing resistant equivalent 35.3, and FN, WRC92. Okay, which means that, what does it mean? I'm sorry. We have two options in order to understand what will be happening in front of the corrosion. Okay, we need to know what is the percentage, what is the quantity of ferrite in our duplex stainless steel. That is not trivial to know that value. So in 1992, the Welding Research Council released a new way to measure this ferrite. But they don't talk about percentage of ferrite. I mean, a physical quantity. They talk about ferrite number. I think that it will be clarified 1 minute, in 1 minute. Okay, so remember that we have a value called percentage of ferrite and ferrite number. Okay, this is important. I'll go over that in a minute. Acetone, etc. Nickel 7%, high percent. Okay, high percentage. And PRE 41.7. This is the PRE of the filler metal. This is very important to be understand. This is related with the filler metal, not related with the weld metal. Okay, to understand, to calculate what is the corrosion resistance of the weld metal, we have to calculate, we have to measure the chemical composition in order to obtain a value. And as we will see in a moment, we can obtain at the end of the weld process, the welding process, 3 different values. One value for the base metal, one value for the heat affected zone, and a third value in weld metal, which is very important, very important. Okay. The acetone for GTAW, if we want to work with Howard is exactly the same. If you see, Harvard offers to you even more nickel, 8.5 to 10.5 nickel, okay, in order to maintain, to promote the generation of austenite, okay. If we see Kobelco from Japan, the same logic, include more nickel. Okay, that's all. It's pretty simple. Of course, we have to do the match between the filler metal and the base metal. That's obvious. That's it's logical. Okay, that doesn't have any, that doesn't resist any analysis of okay. But of course, it's not trivial, but it's quite simple. The most important thing is that that if you understand the role of nitrogen, the role of nickel, you will be success, and you'll be success in your works related with this kind of alloy. Okay. Okay. Let's talk about a little about shielding gas. Okay. Of course, the shielding gas is related with GTAW, with toxic active gas. But of course, we have a flux core shielded, okay, and we have GMAW. So, in normally when GMAW, it's pretty common to use 80% of argon, 20% of CO2. That's all. Okay. The magic is done through the alignment elements. Okay. Pretty good. You have a lot of literature that they recommend you to use hydrogen, helium, nitrous oxide, helium. Well, in general, it's normally an offer from the industrial gas producers. So it's more related with marketing, with than produce through a real experimentation or something like that. So if you check, for instance, let me check one here. If you check this pages, these pages even give you the right mix. For instance, here in Kobelco, if we have to work with the super duplex stainless steels in flux core, we have to work in DCEP, direct current electrode positive, 80% argon, 20% CO2. The all life shielding gas. Okay, nothing special. If you see, for example, the standard duplex flux core, DCEP, 100% here CO2. Okay, so the filler metal is not a problem because it has more nickel. The shielding gas it's not a problem. Pradeep, let me go on your question in a minute. Okay. So the shielding gas is not a problem if we have filler metal. have that clear in your mind. Okay. Okay. This is quite interesting. How much heat input was applied during the welding? Okay. Mm, Probably the most tricky thing when you are welding duplex stainless steel is that the cooling rate must be adequate. And and when I say adequate, it means that it can't be very low or very high. We need a cooling rate enough to produce enough austenite, because remember that these alignments solidify 100% ferritic, okay? And not too much in order to prevent the production, the segregation of the lateral phases. Okay, so who defines, have this in mind, who defines the cooling rate? The cooling rate is depends on the thermal properties of the material, and what is the amount, the quantity of heat that we are that receive the base metal. Okay, this is quite important, and we have to talk about some details here. Normally, the heat input is calculated by the use of the power in the arc of the arc power, which means voltage multiplied by amperage, and divided by the trouble speed, which is a classical, a traditional point of view, but is only applicable, is only usable, is only useful with traditional technologies, which means no traditional equipments with any other special control on the wave. Okay, the very basic equipment not to control the positive wave, the negative part of the wave, the time of during the positive part of the wave, etc., etc. It doesn't exist here. This is applicable only for traditional equipment. If we have to work, for instance, with pulsed arc, we are not able to measure our heat input by the use of traditional equipment. We have to work with an equipment able to give us the quantity, the amount of instant energy which was invested in this welding. Okay. Well, which is pretty easy, because we just need an equipment to read the instantaneous energy, and we divide by the length of the weldment, and we obtain the heat input. This is pretty important. Okay. If we are working with pulsed arc, we can't calculate the heat input just by the use of the classical equation of voltage multiplied by amperage and divide by trouble speed. It doesn't work in that way. Okay. Well, we have some documents that support us with this kind of information. The first of them is section 9 as you know, Section 9 from the BPVC code from ASME, which is about qualification of producers and qualification not only for welders but also for operators. Okay, so there we will find these three gorgeous equations that I'm showing you. Okay. That also is ISO has its own guidelines for measure of welding energies, and it's quite important. And once we have calculate the theoretical heat input, which is related with voltage, with amperage, with travel speed, we have to consider the losses of energy between the electrode and the base metal. Okay, and these losses are quantified by the use of an efficiency coefficient. When you can see here this, I think in English, I have no idea how, I think it's mu equal, it's a value that affect the heat input, okay? This theoretical heat input. And this is quite remarkable because if we see here, as you can see here, only submerged arc welding has a K factor of 1. So if we calculate the heat input in submerged arc welding with the voltage multiplied by current and divide by velocity, this is the only case in which that value is real, because all that power that we have in the electrode is given to the base metal. But in the other case, that's not true. If you see, for instance, TIG welding only is able to take only the 60% of all the power in the arc and carry that power to the base metal. So we lose 40% of the original heat input, which means that at the end we need more power. And I will show you why this is so important. Okay, so real values for heat input using K factor, having in mind the technology of your machine, okay, etc., etc., etc. How much heat input was applied during welding? Again, we have this technical report of ISO, which show us how to calculate and how to measure these welding energies in the field even. Of course, we have a very good document from Switzerland, which is the guideline on how to measure current voltage and arc power in arc welding. If someone wants this document, I can share with you with any problem. Okay, this is the reason because we need this QN. Let me check if I can use a pen here. Check. Okay. Normally, we use this. Let me show. Okay. Normally, we are interested in this temperature, T8/5, right? So we need the thermal properties of our material, T0, which is the initial temperature, the heat input, and that's all. We need this temperature. But in this case, when we are talking about, I'm sorry. When we are talking about duplex, we are interested in this temperature, T12 eighths, okay? 12 eighths. But we needed this one in order to calculate this one. And why this is so important, this time is so important. It's so important because we have to be able to cool our alignment. Give me a second. I think this second one. Okay. What is here? What is here? We have chromium and we have nickel, which is more of the representative elements in duplex stainless steel. Okay. So if we have solid our metal, we rise the temperature, we reach the liquid, okay, and we start cooling our metal, and it solidify 100% ferrite and start cooling up to room temperature, of course. But if this speed is too low, we have a lot of phases, carbides, nitrides, alpha phase, chi phase. Well, a lot of things because we have a lot of alignments. Okay, so we have to heat the material to be able to melt the material, and the cooling rate must be as higher than we don't have these phases, okay, but as lower than we don't have we have enough austenite. So this is very, very important, okay? Of course, as you know, I know you have this information in your mind. We have to consider if we are welding a thick plate or a thin plate, okay? And the difference is if I'm able to weld by the use of just one bead, I'm talking about a thin plate. If not, I'm talking about a thick plate and I need more than one beads. Okay, we are talking about a multi-layered joint. Okay, so my idea is to come here from liquid and don't touch these curves, these noses. Okay, so must be enough to produce austenite and must be very quickly not to touch these noses. Okay, that's all the clue of this material. Of course, it's quite difficult not to obtain at least a little amount of these deleterious phases. Okay, but it's what it is. Nobody wants residues or losses, but the real world is full of this kind of losses. Okay, let's check. Okay, let's advance here. Okay, what kind of shielding gas is used? Why I recommend you to use 2% of nitrogen, 98% argon, or in other terms, in some literature or catalogs or books, you find 2% nitrogen valence argon, which means that the rest is argon. Okay, so here we have in the red line, the red line here is the base metal. Okay, and if you look, this argon 2% nitrogen is almost the same, has the same behavior. Okay, so it's the best option for us. Here, this is part of our research that I finished some in the 1918, 1917, I think. Okay, we work with these three different mixes, and the best one was 2% argon. You have a lot of you will find a lot of recommendations in literature, in catalogs, and whatever, but no one tell you why. Nobody tell you what's the reason for that decision. And in welding engineering, and especially with this kind of material, we have to sustain, to support our decisions in technical information. Okay, that's pretty good. If you see here, even the elongation, the percentual elongation, has it's a product. It's related with the gas, the shielding gas that you are using. Imagine that with 2% nitrogen, you obtain 24% of percentual elongation, and only 16% with 2%, 5% nitrogen. That it's pretty amazing. Because the difference is only 3% of nitrogen. Okay, pretty good. I hope you are following me. Good. Okay, so we decide which base metal we will use. We selected the filler metal. We select the process. We select the gas. And now what happened? We calculate my heat input. We calculate my real heat input by the use of this K factor that we mentioned some minutes ago. And now what? What happened? How could I know if my joint is solid, is it's a good, has good properties? So, okay, so we have to know what is the final amount of delta ferrite in 3 zones: in the base metal, and it's quite simple to know that; in the fused zone, or in the metal zone, on the weld metal; but also in the heat affected zone. Okay, pretty good. Now the question is, okay, how could I know how much ferrite do I have in my weldment? How could I know that? Well, we have some strategies. In this graphic, I'm showing you 2 ways to measure, in fact, to estimate the delta ferrite percentage. One of them is ASTME 562, which is a statistical procedure that allows you to find a confidence interval in order to know what where could be your real value. Okay, forget okay, let me, please follow me here. Please check this box here. Okay, this is the base metal, the original base metal. Okay, when we estimate my delta ferrite by the use of ASTM E562, we obtain 35 in average. This is my average value, okay? 35. Sorry. $36, okay? This is the value of my base metal, right? And by the use of 2% of nitrogen, 98% of argon, we obtain this value, 49% of ferrite, okay? Which is not bad, because we are between two limits, okay? The first, the lower limit of this delta ferrite is APITR 938Z, which allow you to obtain 25% as minimum to consider that your work was well done. But also we need an upper limit, and the upper limit is 60%, which comes from the same with the same standard. Remember, API, American Petroleum Institute, TR 938Z. Okay, pretty good. This is amazing. We select we select the filler metal, a base metal, blah blah blah. Okay. Now we are evaluating the result, and this evaluation of the result, it's quite important for the qualification of our procedure. Okay. So if we take, for instance, ASME section 9 from the boiler pressure vessel code, which is aimed to guide you with the qualification of your process, with the qualification of your staff, there you don't won't find any information about these things of these details. They tell you, okay, you need 2 tension tests, 4 guided vent tests, whatever. But remember that who rules on over this section 9 is the construction code. Okay, so the construction code gives you all these little details, and if the construction code doesn't mention anything, you have to talk with your client and ask him, okay, what is your need, and try to find the best solution for him. But you need to be to know that is very important to measure the proportion, the ratio between ferrite and austenite. Okay, this is the case of the fused zone or the weld metal. Okay, the fused zone or the weld metal. But also we need to know that the most has in the other welding process, we are a concern about the heat affected zone. So we want to know what happened with the changes that we produced in the heat affected zone, and we have two options. If you trigger the show, we cannot continue further because the t-shirt complete. Oh, I'm sorry. I'm sorry. I have enough time, or I have to cut here. Sorry, can you hear me?
Please continue, please. Yes, yes, I can hear you. Please continue.
Okay, thank you. Thank you. I think that my time was over. Thank you.
You can continue.
Okay, so we have evaluated the base metal. We have evaluated the weld metal, but our main concern is what happened in the heat effect zone. So the only method that it's useful for that is to use ASTME 562, which consists in taking a bidimensional information, try to project in a volume this characteristic. I mean, we count because it's a process of count grains of ferrite, grains of austenite, grains of ferrites, grains of austenite, and try to obtain obtain a confidence interval. Okay, with a plus and minus error. Okay, it's pretty common in statistics. This is it's obvious. And this is the main restriction that we have when we try to use a ferritoscope in order to know what is the amount of delta ferrite that you have in our welding. Because the heat affected zone is it's very thin. It's hard to know where it starts and where it finish. You know, so it's from my point of view, it's almost impossible to measure what is the amount of delta ferrite with the ferritoscope in the field. Unfortunately, the field implies that we can't destroy our welded joint to do a measurement. So this is very important. Your procedure, your welding procedure specification must be published in the shop, and people have to be clear that if they don't follow that procedure, there will damage the work. There will obtain whatever less than we need to obtain. Okay. This is very important. Very important. Just a little change in the heat input implies a change in the cooling rate. A change in the cooling rate implies that probably you have less time that needed to obtain the expected amount of austenite, or that you obtain you have a cooling rate too long, right? So you have a lot of deleterious phases. Okay, she alpha, carbides, whatever. So all of what is the problem with that? With those phases that they um, how can I say that uh, they damage the thickness. They are a source of lower thickness. Okay, they are fragile. They are they have high hardness, but is not good, and especially because when these phases appear, they are eating our alignment elements, and those alignment elements must be in the align, not in these phases. Okay, very good. Okay, so this is our main concern. What happened in the heat affected zone? And as in the previous case, we have a lower limit, which is 35%. In this case, my reference is NACE, okay, NACE, and the uh, the upper the upper limit is 65, okay. So if my amount of delta ferrite is between these two limits, we are we have done a good job. Okay, and again, the best option is to measure the delta ferrite during the qualification process, not during the welding in the field, but in the qualification of the procedure. Okay, use ASTM E562. Okay, very good. Okay, now let's talk a little about distortions. Okay, we know that if we compare carbon steel with stainless steel, the stainless steel is it's more, I think that the word in English is prone. It is expected to have more distortions in stainless steel than in carbon steel. And the reason for that is the relationship that exists in the physical properties of our base material. And the base equation that we have in mind is this one. The distortion is proportional to this relationship. So if we have a higher Young model and a higher conductivity, we have lower distortions. And if we have a higher expansion coefficient, thermal coefficient, of course, we will find at the end of the day more distortions. So the main idea here is that in duplex stainless steel we will have less distortion than those expected in austenitic stainless steel. Okay, which is a very good news for us. But of course, we have more distortions if we compare duplex stainless steel with carbon steel. Okay, very good. Let me check. Okay, the interpass temperature is another thing that we have to have in mind. If you remember, let me check here. Here, when we try to calculate this temperature called 8/5, right? We take into account this T0. This T0 where was the initial temperature of our base metal. Okay, so another basic idea, fundamental idea, critical idea. We never preheat duplex stainless steels. Of course, there is an exception. If we are, for instance, in Canada and we have to weld at -20 Celsius, of course, we have to rise that temperature at least to 20, 25 Celsius. And if in that case we need to preheat, okay, go ahead, preheat, but not too much, okay? And as we mentioned in 1 minute ago, we need this initial temperature, okay? So this initial temperature is related with the preheating, of course. Let me come back here. Okay, so this interpass temperature obviously is related to multi-layer welding with thick plates or pipes or whatever. Okay, just we have to have in mind that it's necessary to control the temperature interpass. How can we measure this temperature? The best options are thermocouples. Thermocouples, not crayons, not infrared thermometers. No, thermocouples are the best. Okay, and this temperature, if this temperature is related with the cooling speed, we have to control this interpass temperature. Okay, what is the limit? Which is the recommendation? Remember that as higher the alignment, or as higher the level of alignment, as lower the interpass temperature. So in duplex, which means the first members lower alloy in the family of duplex stainless steel, we can use 250 Celsius. If we talk about super duplex and duplex, we can talk about 150 Celsius. Okay, 150. And in the case of hyper duplex, the recommendation is 100%. Okay, 100%. This is very important because this interpass temperature becomes into this T sub zero. T sub zero is related with the cooling rate. The cooling rate is related with the amount of austenite, and as you remember this this relation between all the variables and the process, it's true. We have to consider everything, try to do our best in order to control our welding process, and that means to control base metal, that means to control the filler metal, the shielding gas, the procedure, the qualification of the welders, the way in which we measure ferrite, etc., etc., etc. Okay. Okay. Great. Amazing. Okay. About the electrical parameters, which means basically voltage and current, we have a lot of information. Of course, if we are consistent with everything that we have mentioned before, we have to be careful that the heat input calculated here with these parameters are between the cooling rate that I need. Because remember, the heat input define the heat input and the thermal properties define what is the cooling rate. The cooling rate defines what is the final metallurgical properties. These metallurgical properties define what is the behavior of my duplex stainless steels in front of a corrosive environment. Okay, so we have a lot of information, but good information. This, for instance, is taken from the IMO, the International Molybdenum Association. We have a lot of information, valuable information, not commercial information. Take care of that. Not commercial information, but technical information from the IMO and the Nickel Institute. Okay, the Welding Institute, of course, has beautiful information. The International Welding Institute has amazing information. The Welding Handbook could be a good source of information. Okay, just I want to stop here. Ultrasonic dissemination and weld on base metal. Yes, it's possible to use, of course. As you know, for instance, if you want to qualify a welder, you are authorized. Well, if it's allowed by the construction code, the construction section of ASME, you can qualify the welder by the use of ultrasonic examination or ultrasonic or radiographic testing. No. So yes, it's possible to use ultrasonic. It's more or less the same than work with in that sense. That it's more or less the same to do ultrasonic to ferritic, martensitic, austenitic traditional alloy of in stainless steels. Okay, pretty good. Preheating? No preheating. Please don't do that. Considering like 6 to 8 millimeter for, well, I don't know what it's talking about. People in the chat. Okay. As I mentioned before, it's really, really hard not to obtain at least a little amount of these phases, which means carbides or chi or alpha phase, well, it's a little hard to 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 obtain 100% ferrite and austenite. No, absolutely clear. No, it's quite difficult. So we have in terms of our construction code, we have to check what is the maximum amount allowed of this kind of phases. Okay, 0 is too hard to obtain. 0, it's too hard to obtain. It's almost impossible, and even it's hard to see in to detect this kind of phases. Okay, it's really hard to know what is wish is wish. Okay, so this ASTM A9023 help us to detect this kind of phases. Okay, so if the work is I mean the risk associated of the fail, no, not the fail, the fail of this project is could be catastrophic. So we have to be concerned about all of these elements. Okay, very good. I'm so sorry. Sometimes my English is not enough good. Okay, pickling and passivation, and I think we are finishing. Please tell me when I stop, because I have a lot of things to say, but I don't know if we have enough time. Okay, pickling and passivation. Right here, you can see these beautiful colors produced on the surface of a hyper duplex stainless steel. This is the color produced by 2% of nitrogen balance argon. Okay, these beautiful colors here. Okay, but we don't need those colors. We need a clean surface without these oxides. These colors are the proof that we have oxides there. So we have to develop, to set up, uh, to make the pickling of this stainless steel. Normally, this is possible by on the face, not on the root. Okay, because normally it's impossible to access to the root once the weldment has been done. Okay, so we need to pickling the surface in order to retire this coloration, this tinting. Okay, and we have to passivate the surface in order to obtain a new layer, a solid layer of oxide, chromium oxide, which is the skin that protect our duplex stainless steel. Okay, here we have a typical joint. This is, of course, again, this is an hyper duplex. You can see what is the change produced by the heat, by the thermal cycle in our base metal. In the heat affected zone, we can see all these these tiny grains here. Okay, and in the weld metal or the fuse zone, we have this kind of islands, which are very interesting, as we can see in a moment. Okay, pretty good. This is This is pickling. This is the pitting. This is the pitting that we have. Simply the ferrite is dissolved and the austenite is resisting. So this is the reason, because we need enough austenite. Okay. Well, another thing that we have to mention here is that during the welding cycle, we can lose nitrogen. We can lose nitrogen. Okay. So if we lose nitrogen in the PREN, if this value, the most important in that equation, if we lose that original quantity of nitrogen, we decrease, the PREN will be decreased. Okay, so we will have a PREN in the base metal, a PREN in the heat affected zone, and the PREN in the weld metal. Okay, so this is another reason. This is a new reason to facilitate the generation of new austenite by adding nickel or by adding nitrogen in the shielding gas. Okay, very good. Okay, and we have been talking about pitting resistant number, equivalent number, right? We talk about PREN, including nitrogen, but also PRE, including wolfram or tungsten. Okay, but this is related with pitting. Pitting is like a little worm eating our metal. Okay, it's like a little perforation. In some cases, it's very hard to detect it up to the catastrophic failure. Okay, so this is critical to control this pitting. But also we have another phenomena which is even worse, or could be even worse, than pitting, and it is the crevice, resistance temperature. Let me show you what I'm trying to tell. Okay. In a moment, we will follow with this previous idea. We know that we have a lot of constitution diagrams like this one, okay, which were designed in order to predict how many delta ferrite we will have after our welding, right? Based on the chromium equivalent and the nickel equivalent. Okay, so there are a lot of these diagrams, a lot of them, at least 10, 9, 10, but it is possible to use these diagrams to predict what is the final amount of delta ferrite in my joint. Is it possible or not? Well, what is the position, the official position of the Research Welding Council to use this kind of constitution diagram? Is like to try to predict the weather. It's like predicting the weather. It could work, could be useful, couldn't be useful. Okay. So it's a guide. Yes, they are a good guide, but not necessarily the best. In this case, I'm showing you the all the mathematical models that I used in the research some years ago. And one of the pretty common mistakes made by engineers interested in this topic of duplex stainless steels is to use the Schaeffler diagram in order to predict which is the final amount of delta ferrite. It's a very big mistake because if you see here in the upper part of the table, you see that doesn't matter which model do you take, more or less the final value of chromium equivalent is more or less the same: 31, 31.3, 31.9, 33.7, more or less the same. But if we calculate nickel equivalent, we can see that if we use Schaeffler, the value of Schaeffler is 7.7% of nickel equivalent. Why? Because in the mathematical model, Schaeffler doesn't consider the role of the nitrogen as an stabilizer of austenites. Okay, so it's wrong. Not use Schaeffler. Please don't use it. Okay, it's better to use the long, because the long modified Schaeffler. This is the reason. This is the reason because we have a constitutional diagram called Schaeffler DeLong. DeLong modified Schaeffler, and of course, considering in this equation the role of the nitrogen, but in a classical Schaeffler diagram, we won't find nitrogen. Okay. Okay, there are a lot of others diagrams. The most interesting could be the Schaeffler DeLong modified, which is called the Outokumpu diagram. We will see that diagram in a minute. So take care when you are trying to predict the delta ferrite, especially when we are trying to weld dissimilar metals. This is very useful, this diagram, but we have to know how to use it and when to use it and when not to use it, which is more interesting, even more interesting. Okay, this green one is the Outokumpu, and as you see here, we have chromium equivalent, of course, which is expected. Chromium equivalent and nickel equivalent will be here. Okay, and here you can see the equation and the role of nickel, of nitrogen. So it's pretty good. It's pretty accurate, this constitutional diagram, but nothing is perfect. If you see here, you will see that this diagram works with Fn, with ferrite number, but the ferrite number is not necessarily equivalent to the percentage, the real volume of austenite or ferrite in our material, or in our heat affected zone, or in our weld metal. Okay? Basically because it is related with them. Well, it's a little hard to explain that, but the main point is that one real thing is the volume of ferrite expressed by the use of a percentage, okay, 20%, 30%, but we are talking about something real. And ferrite number is, from my point of view, just a source of confusion between the people. Okay, very well. So in this case, this is the result that we found welding these hyper duplex stainless steels. Here we have the SP diagram, which is another one, is a modification of the other diagram, and works pretty well. We have 35.9, and with Autocompo we obtained 35.7, and this was pretty close to the value that we obtained by the use of ASTM. If you remember, we mentioned statistical methods that allow us to obtain a confidence interval in order to know which is good value for our ferrite. Okay, because if we have the amount of ferrite, we can calculate the percentage of austenite, of course. Okay, very good. How it works? We just calculate chromium equivalent, nickel equivalent, and there will be a point in which these two values will cross, and we calculate based on the slope what is the amount of delta ferrite. Okay, very good. This is here. You can see the difference between the percent of or ferrite and the ferrite number. Okay, both of them starts in 0. If you see here, 0, but as this ferrite start growing, the ferrite number lose this linear relation. Okay, this 1 from 0 0, we start in 0 0, but 38% real percent of ferrite represents 16 ferrite number. It's a number. It doesn't have any unit. It's just a value. Okay, but here we expect to physically to have 30.8% of delta ferrite. Okay, we have some limits This is the classical line of austenite martensite, which comes from the Schaeffler diagram. We will have here full austenite plus ferrite, all this zone here, all this based on the chemical composition. Okay, this is an old topic. This Schaeffler comes from the 40s, 1940s, and now we have some new diagrams. Okay, so this is another mistake, pretty common. People said, "Don't worry, I'll calculate, not estimate." We have been doing estimations. Remember that estimations. Some people will tell you, "I can calculate the ferrite for you," and that's not real. At least not real or not possible for welding, because it's very expensive to how can I say that? How to obtain an accurate ferrite ratio by the use of a heat treatment. Yes, this is useful. This equation, this percentage of ferrite is useful just in case of not weldments, but well, I forgot the word in this moment, but come on, it's not forgings, it's well, this is useful for the first member of the family of duplex stainless steels. Not weldable, but aimed to be used as I forget the word. Okay, so it works more or less the same. We calculate the chromium equivalent and nickel equivalent, and that temperature of temper annealing. Listo? This is very important. The temper annealing, which is between 1050 and 1150. Okay, but this is not for welding. So take care with that. Oh, pretty good. This is the PREN. Oh, well, there is a question here is, okay, but if the pitting resistant number is just a kind of number useful to compare members of the family of duplex or duplex and austenitic and ferritic alloyments, this is really useful. I mean, this PREN works for someone, for something different than to to do these comparisons, and the answer is yes. There is a linear relationship between, as you can see here in this slide, between the PREN or heating resistant number and CPT. Okay, CPT. This is very important. Okay, because CPT is a critical temperature for pitting, which means at which temperature is pitting expected Okay, so this is very real. I can take a thermometer and measure the temperature and to know if we will have or not pitting. Okay, very good. Okay, I think I'm finishing. Okay, this is pitting under the microscope. Okay, pitting is a very, very low quantity of loose material, lost material, but in a tiny zone. So this is critical because it's a kind of direct perforation, and the damage is simply catastrophic. It's really hard to contain that, to control that. Okay, so this is the problem. Pretty good. So here another recommendation for you. It's in duplex stainless steel is absolutely it's not allowed, is prohibited, is mandatory, doesn't have arc strikes, is not allowed to have sparks. I can't remember that word in this moment. It's not sparks. Is spotter. The spotter is not allowed. Why? Because if the spotter hits the surface of our beautiful duplex stainless steels, we will have a little zone which will be cooled very, very quickly, and we don't have any austenite in that point. So is the perfect point to get pitting. So is not allowed spatter or even arc strikes. Okay, this is very important to know. Okay. Let me show you. I think I have some. This is pitting, of course. This is the base metal. This is hyper duplex stainless steel. This is a very tiny sample. I think from here to here it has 12 millimeters or something like that. So this you can see here the the damage produced by pitting during test, of course, not in service. But this yeah, this happened in service. This is a very beautiful picture from Autocompo. Okay, and here is how you can see the corrosion in a duplex stainless steel. The ferrite is dissolved, and the resistance of the corrosion is done by austenite. As you can see here, it's a kind of island of austenite. Okay, so these closed zones by austenites are pretty good in order to. So ISTM G44, the temperature for, I don't know where you can see. This is a kind of island, but this island was broken here, and the ferrite, the delta ferrite, was dissolved. Okay, this is the problem with the with ferrite, and we have another problem related directly related with corrosion, which is crevice corrosion. Crevice corrosion happens when we have two faces in contact. Okay, so it's a face against another face, as in this picture. Okay, two plane surfaces, one against the other one. Okay, imagine that in order to, well, we have mentioned that the chromium oxide, which is the skin of our stainless steels, is produced by the oxidation of the chromium in the alloyment, right? So, if for any reason this layer is damaged, naturally the reaction between my base metal and the oxygen of the atmosphere, this reaction will produce a new layer, a new passivation layer. But what happens if we don't have any oxygen? Without oxygen, we don't have oxides. If we don't have oxide, we are not able to protect, to reconstruct the layer of chromium oxide. And this is what happens when two surfaces are in contact. There aren't any oxygen between them. So this produces a corrosion not localized like in the case of pitting, but the degradation of a very big surface, very big. So this is another catastrophic fail. Okay, what's the problem with this crevice corrosion, which is called this corrosion process between two plane surfaces in contact? What's the problem with this crevice corrosion that is invisible for us? We know that what crevice corrosion existed because of the catastrophic fail. Okay, which is very dangerous. Okay, good. Let's check this graphic, which is very interesting. In red, you see the CPT, which is the critical pitting temperature, and you can see in blue the CCT, which is the critical crevice temperature. So this word critical means that at this temperature we will have certainly pitting and certainly crevice corrosion. But what's the problem? With the lower loss of material, a pitting corrosion can destroy a duct, a work, a plate, okay, with a very, very, very little amount of material deteriorate, we will have a catastrophic event. The advantage is that this pitting corrosion is higher than the critical crevice corrosion. Okay, this is the advantage, but the problem is that CCT is lower. At the same time, is an advantage and disadvantage. Okay, so we have to evaluate in our project which is more important for us, for our client, for the application. The probability is to be exposed to pitting, or the probability is to be exposed to crevice corrosion. This is quite important for us, okay? Because we have to put our, how to say that, we have to focus in CPT or CCT, okay? Very good. Okay, I think I have one or two more slides. What happened with the stress corrosion cracking? The stress corrosion cracking is a concern with austenitic steels, as you know, which means that we have cracking, but at the same time we have stress, and at the same time we have some up to a point corrosion. So is the situation in which we have stress, which is always present because of are enough the residual stresses, but also corrosion, because of course if we are investing time and money in a duplex stainless steels, is because we are exposed to any kind of corrosive substance, or yes, liquid, vapor, solid, whatever. Okay, and cracking because the damage is enough to break the material, like a little little cracks. Okay, so stress corrosion cracking is a concern in austenite, but the good news is that it's different when we are facing stress corrosion cracking in ferritic stainless steel. Ferritics are very, very strong, and they can resist a lot of stress corrosion cracking, up to the point that they don't mind this kind of stress corrosion cracking. But this, for us in super duplex stainless steel, it's not a concern. Okay, stress corrosion cracking is not a concern. Good, pretty good. Well, there are a lot of different tables about how to select a specific base material in terms of which is the environment, because remember that ASTM A48 is just to evaluate the behavior of these alloys, but in presence of a solution of 6% of ferrite chloride. I can't. I don't. I don't have. I can't remember how to say that. Ferrite chloride, ferritic chloride, at 6%. Okay, but it's not the real word. Now we need this kind of material because we'll be exposed to a specific substance. Okay, so this specific substance will be evaluated in front of our material. Very good. Okay. And the final recommendation is to be patient during the metallographic preparation. You will need a good metallographic preparation if you want to measure how much ferrite do you have, if you are using, for instance, a software to measure this ferrite, or you will need a very good preparation if you are interested in use the ASTM 563, I think. And it's not trivial to prepare micrographs, okay? Because the material is hard, the material is extremely resistant to corrosion. So to pick this solution, this material, it's a little tricky. So my best recommendation for you is to use Beraja 2, which is a solution which is made with water, hydrochloric acid, biofluoride ammonium, and a little more of potassium. And that's all. You dissolve everything and you will be happy. Okay? But it's not trivial. You have to there is a learning curve in this kind of material. Okay? Then, very good. So, let me finish. We will now understand the graphics that we see at the beginning of this conversation among colleagues. We mentioned that the nickel was pretty interesting, very important, as well as nitrogen, because they have a direct relationship between PREN, the CPT, and CCT. Okay? But also, this amount of nickel and nitrogen is related with the strength and ductility, because if we don't have enough austenite, we will have less ductility, because ferrite is less ductile than austenite, right? Okay. I think, okay. Austenite and delta ferrite is, of course, related with the microstructure. Of course. And obviously are related with the strength and ductility, because at the end of the day, the strength of our alloy is the strength of the austenite and its proportion plus the resistance of the austenite multiplied by its proportion. So it's not the same as we see to work with a ferritic, 100 ferritic stainless steel than to work with 100% austenitic, and very, very different than work with duplex stainless steel. So everything is related, okay? Now, the actual heat input, as we mentioned, has a directly relationship with the microstructure because, again, heat input define the cooling rate. The cooling rate defined the amount of delta ferrite. The amount of delta ferrite defines the amount of austenite. The amount of austenite and delta ferrite defined the mechanical properties. So everything here is related. There are no things that we can I think that there is an expression in English for that. You can't cut corners. You have to consider everything in a very, very careful way. Okay? Very good. The constitution diagram as we see is possible. Its use is possible if they are accurate. Of course, they have limits. They are not perfect. We need probably we can show you in another conversation how to work with these diagrams, which is interesting. It's not quite difficult, and it's pretty useful. And finally, the chemical composition is very important. As we mentioned, the original amount, the original quantity of nitrogen is lost during the thermal cycle. Okay? So if the nitrogen at the end is not the same than in the beginning, we will have a new pitting resistant number. And a new pitting resistant number means that we have damaged our material. So remember, the main goal when we are working with super duplex, lean duplex, hyper duplex is not to damage or to produce the lower possible damage in our base material. So this is the last slide.
Yeah, thanks,
This is the final.
Alberto, for this wonderful presentation. I think
And
you covered it in depth with lot of practical, aspects. And we have received a lot of questions in the Q&A session. Okay, but considering the time scarcity, what I will do is I will send you all these questions in mail. Yeah.
yes, thank you.
Yeah.
Thank
so
you
you
very
can
much.
answer those, and then we will share this with the party.
I hope you enjoyed this conversation. Very glad to having here with you, with all of you. And well, thank you again. Thank you,
So one of
Dr.
the, I would say one of the best technical talk on duplex in this platform.
Oh, well, thank you. Thank you very much. Thank you very much. Thank you very much.
So we will
Uh,
send you all these questions. You can answer them back, and which we will share with the participants along with the recording of this presentation.
Certainly will be a pleasure to answer all those questions if if is possible for me, because as I mentioned, nobody knows everything, but it will be a pleasure. And thank you again, and
Yeah.
well, have a good weekend.
Yeah.
Thank you very
So
much.
on behalf of Indian Institute of Welding, we extend our thanks to you and also to all the participants. I think during the peak time, we had more than 170 on board today. So it's time we sign off. Yeah. Thanks. Thanks everyone. Bye.
Okay. Thank you. Thank you. Bye bye. Blessings.
Bye.